Good morning, grade 10s. How are you guys doing today? Welcome to our 7th lesson in physics. This is grade 10 physics. This is your teacher, Marshall A.C. Candiado. I hope you guys enjoyed the long weekend. Today we're going to be looking at the topic tanning effect. Tanning effect, sometimes some may even go on to say tanning effect of forces, right? But tanning effect. And what are the objectives? What are we supposed to be able to have learned or supposed to know by the end of this lesson? By the end of this lesson, you guys should be able to describe the moment of a force. You should also be able to identify the load, effort, and fulcrum in everyday examples of common machines, right? So as we go through the lesson, you will see some of these common machines that we are referring to. We should also be able to use conditions of equilibrium in simple calculations. What we'll do in this lesson is that we'll mainly talk about how we have the concepts or the principle of moments, where we have clockwise moments and anti-clockwise moments, and how you sometimes have them being in equilibrium, right, where the clockwise moments are equal to the anti-clockwise moments. But then this information can then be used in actual calculations. So this is lesson 7. In lesson 8, we will focus mainly on calculations that have to do with tanning effect. Okay? So as always, please just pause the video for just a few seconds for you just to look at the objectives that we're going to be dealing with today. Okay, so like we say, today we're going to be looking at the concept of tanning effect, and then the first thing we have to talk about is a moment. And it's written here that a moment refers to the tendency of a force to rotate or twist an object about a point or axis. Right? The point or axis of rotation is known as the fulcrum or pivot. So if you've ever seen someone using a spanner, right, to maybe try and loosen a wheel nut, there was actually a moment that was being used there. There was actually the tanning effect. When you're tanning the spanner or when you're tanning a screwdriver, you actually have a moment. That's what we call it. It's called a moment when you're using that screwdriver or a spanner, or when you're tanning, anything about a fixed point, right? So I remember in some of the previous lessons, we also looked at the concept of momentum, and I hope you recall the unit that we used there. You will find some similarities between the momentum and the moment of a force that we're going to be dealing with today. So what I'm going to do right now is we're going to play a short clip that will show you some simple illustrations of what we mean when we say a moment. Okay, so let me just put it there.
Think of a spanner loosening a fixed nut, or a child on a seesaw, or a door opening around a fixed hinge. All of these things are connected by something called moments. A moment is the turning force around a fixed pivot. The pivot is the nut, or the middle of the seesaw, or the hinge. We can have one moment acting, which results in a turning force.
Okay, so by yourself you can play that video, that section of the video. You can rewind this video so that you can watch that again. But basically, that is what a moment is. So when you have a spanner and you're trying to either to loosen a nut, right, and then you're turning it. If you've ever loosened a nut, right, when you're turning it, or the simplest one, the one of the kids on a seesaw, right, this one, where this kid is on a seesaw. Do you know a seesaw? I hope you played with seesaws when you were in kindergarten, and some of you are probably still playing on seesaws even up to now. But the idea is that when this guy is sitting on the seesaw, it's going to turn around what we call a pivot, okay, is going to turn around what we call a pivot. So I just fast forwarded it so that you can have two people, because you'll be wondering why is this guy playing alone on this seesaw, right? So usually what will happen is that when this person, this one, right, sits on this seesaw, and then it causes the beam to move up and down if this one is also on the other side. But this beam is actually turning around this pivot, the center, right? And that is what we actually call the moment, right? Then you have the moment that is being experienced in that particular case. So generally, the moment would be a measure of a force's turning effect. Okay, so the moment of a force, turning effect of a force, to say the moment, to say to which extent are you actually turning this particular spanner, right? And you will find that the moment is a vector quantity. The moment is a vector quantity in the sense that you have the size of the force that you are applying on the spanner, and also the distance of the spanner from the pivot. The distance of the spanner from the pivot. Or here, if you see this boy, he's sitting with a weight of 500 newtons, but there's also a distance that he has from the pivot. The center of this seesaw is the pivot. So when you want to calculate the moment, right, and we're saying a moment is a vector quantity, and we know that vector quantities have both size, magnitude, and direction. Okay, so this one is going to have the force of 500 newtons that is acting downwards, and there's also a distance that is going to be there. So it's a vector. It's a vector quantity, which will then have the unit. Let's see what the units will be. Measured in Newton meters. Measured in Newton meters. So when we talk about turning effect, and we talk about the moment of a force, the moment of a force is measured in Newton meters. Then we will also talk about how, or we're actually going to talk about it right now, we'll not talk about it later. Moments can be clockwise or they can be anti-clockwise, right? They can be clockwise. If you look at your clock, I hope you know the direction when we say clockwise and then when we say anti-clockwise. Yes? I hope you know that. So right now, let's just pause the video again so that you just get to look at these points to say what the moment is. There's a part there that says another moment, another name for the moment is torque. Okay, you can just read up on that by yourself. It's not really necessary at this stage, at this level, but it's good information for you to know. It's good information for you to know. So you can just pause the video and look at more information that we have about the moment. Okay, so welcome back, guys. Alright, so before we proceeded in talking about how we get to balance forces, it's necessary that we just get to understand some, or to recognize or appreciate some of these common machines that we were talking about. Here we have an image where we have a wheelbarrow, a wheelbarrow here. This is also a spanner. Yes, this is a spanner if you didn't know what a spanner looked like. A fishing rod, someone pulling a box, right? And then we also have a bicycle gear, and then a donkey that's supposed to be pulling a load, but I think the load has now ended up being heavier than the donkey, and has now ended up lifting the donkey itself. Okay, so when you have these common machines, these are common machines. You use a fishing rod when you go fishing, the wheelbarrow when you carry different loads. So what is important is for you to identify, to say, okay, on this machine, which one is the fulcrum, which one is the load, and where is the effort. The fulcrum, the load, the effort. You should be able to identify those things. You will find that with different machines, the effort and the load will be at different positions, right? If we were going to do machines in detail, we would have talked about first order machines, second order machines, and third order machines, where you have first order machines maybe having the Lord being in the middle, as exemplified by this wheelbarrow. You have the Lord being in the middle, and then the pivot is usually it's the pivot that's in the middle, because we usually give the example of the seesaw. But in this one, you have the Lord is actually in the middle, and then the pivot is at the wheel, and then the effort is where you'll be pushing, where you get to lift the wheelbarrow. That's where the effort is, right? So we're saying sometimes you can have the effort not necessarily being at the end, right? Sometimes the effort can be in the middle, as exemplified by this one of the fishing rod. With the fishing rod, if you hold the fishing rod, your effort is actually in the middle, right? And your pivot is where you actually holding it, right? Where you will be, where your fishing rod is anchored. Sometimes the fishing rod is anchored on you whilst you're holding it, or if it's bigger machinery, then it can even just be anchored in a big boat. So the effort, the Lord, and the pivot are always going to be there, but they might be in different positions depending on the type of machine that you are using. Okay, so in this case, the donkey should be the one that is applying the effort, and this should be the Lord. But now it's turned upside down, because the effort is the Lord has ended up being greater than the effort, and now the Lord becomes the effort, right? The wheel remains the pivot in either ways. So this is a bicycle gear. If you've ever rode on a bicycle, and that will be your effort. The center of the gear there will be your pivot, right? Now let's look here at balancing of moments. So we say a moment has two possible directions. A moment can either be clockwise or it can be anti-clockwise. And these clockwise moments and anti-clockwise moments, let's just think of it in relation to the seesaw. When you have the clockwise moments, when one person sits on one side of the seesaw and they are applying what we call a clockwise moment, and the other person sits on the other side of the seesaw and they have an anti-clockwise moment. If these two moments, right, the weight of the person on the right side of the seesaw and the weight of the person on the left side of the seesaw, and the distance that they have from the pivot are equal, then you say they are balanced, right? To avoid confusion, I think there's a video that is here as well, just a simple illustration. Let me just play that.
Moment acting, which results in a turning force. Or if something is balanced or in equilibrium, the moments are equal and opposite.
Okay, so if something is balanced, the moments are equal and opposite. As you can see, the two boys on the different sides of the seesaw, right? Let's just push it a bit further. You observe how they actually have different weights. They have different weights, but still they will end up having equal. The anti-clockwise moments will end up being equal to the clockwise moments.
To be balanced, this lighter child needs to sit further away from the pivot, and the heavier child needs to be closer.
Are we still there? So we have one child having the weight of 500 newtons, the other has a weight of 1,000 newtons, right? If you're here on Earth, that means that kid has a mass of 100 kgs. Sure. Right? But then, in terms of clockwise moments and anti-clockwise moments, for you to get this kid will be moving in this direction, that is anti-clockwise. He will be moving this one on the right side, my right? He will be moving effectively in a clockwise direction. He's moving in a clockwise direction. He is moving in an anti-clockwise direction. So when you multiply his mass times the distance from the pivot, you will find that this is 1,000 Newton meters. When you multiply his mass times the distance from the pivot, because he is closer to the pivot, his moment is also 1,000 Newton meters, which means that the anti-clockwise moments are equal to the clockwise moments, if you observe.
This is because the size of a moment is determined by the force and a distance.
Okay. Right. So when you have the clockwise moments being equal to the anti-clockwise moments, the resultant turning effect, there will be no resultant turning effect because they are now balanced. Right? If they are balanced, then there is no turning effect. But when you have one of the moments being greater, if the anti-clockwise moment is bigger than the clockwise moment, then the object will move anti-clockwise. I think this is very simple to understand, right? If you just read these simple points, it's very simple to understand. If the clockwise moments are bigger than the anti-clockwise moments, then the movement will be clockwise. The turning effect will be clockwise, right? Because the clockwise moment will be bigger, right? So this is what the principle of moment states. If clockwise moments are equal to anti-clockwise moments, then the system is in equilibrium, right? Then the system is in equilibrium. Clockwise moments will be equal to anti-clockwise moments for a body in equilibrium. So if we say a body is in equilibrium, and we say this body, this entire system is in equilibrium, and we show you and we say, so the anti-clockwise moments were 5,000 Newton meters. What were the clockwise moment? What is the size of the clockwise moment? Then you just know that it's also going to be 5,000 Newton meters because they are equivalent. Right. Then what is also important is how you get to calculate the moment of the turning effect, which depends on the size of the applied force, as we saw here, right? The size of the applied force, if we look at the boy here, this is the applied force. When we're talking about what does the moment, the size of the moment depend on, it depends on the size of the applied force, in this case 500 newtons, and the distance from the pivot. The distance from the pivot. So you'll find that if this distance was to be increased and it becomes 4 meters, the size of this moment will actually also increase, right? So even though the weight of the boy remains the same, if his distance from the pivot increases, you will find that his moment is also going to increase. And let's say it becomes 4 meters. That will become 4 times 500, which would be equal to 4 times 500. That would be equal to 2,000 Newton meters. Think of this in relation to what we call a fulcrum, or those pivots. A fulcrum, when you want to lift a heavier load, right? But you then use maybe a plank and you place it under a big rock, and then you can move the rock, right? The effort that you've applied is actually being multiplied by the distance of the fulcrum of the plank. And in my imagination, I'm just having the idea of a wooden piece, a piece of wood, where you place it under a big boulder, and then you can move the boulder, right? If you try to move the boulder with your hands only, you can't move it. But then when you place that piece of wood under it, and then you move it, right? Because the piece of wood has a big distance, has a long distance, and it is now multiplying your effort. That's what all machines do effectively. They multiply our effort. Okay? So, moment of returning effect depending on size of applied force, how far from the fulcrum or the pivot the force is applied, right? Distance must be in meters. The distance must always be in meters. When you're doing these calculations, observe that we say the answer or the size of the moment is in Newton meters, so your distance must be in meters. If you are given a distance in centimeters or in kilometers, then you must convert it and change it back to meters. So that's the formula for a moment. Moment equals to force times perpendicular distance from fulcrum or pivot. Okay, so let's just digest a bit of that before we conclude the lesson.
Or in equilibrium, the moments are equal and opposite. To be balanced, this lighter child needs to sit further away from the pivot, and the heavier child needs to be closer. This is because the size of a moment is determined by the force and a distance. So the moments of the lighter person is 500 newtons multiplied by 2 meters, 1,000 Newton meters. And the heavier person is 1,000 times 1 meter to also give 1,000 Newton meters. They're perfectly balanced on their seesaw. Did you notice that moments are measured in Newton meters, Nm, because force is measured in newtons, N, and distance in meters? Note that the distance must be the perpendicular distance from the pivot to force. Here's another example. Can you work out what moments the woman is applying to tighten the wheel nut? Pause the video and work it out.
So you can also just do the calculation. It's a very simple calculation. What's happening there? So you have a force of 10 newtons being applied, then the distance on which is applying to the spanner to move the wheel nut is 30 centimeters. So if you can just do the calculation by yourself, the answer is going to be shown just now, but do the calculation.
Did you get 3 Newton meters? Were you careful to change the 30 centimeters into meters? We can also place this formula into a formula triangle. Force equals moments divided by distance. Distance equals moments divided by force. And moments, as we already know, is force times distance. Here are 2 more questions for you to try. Pause the video and work them out.
Okay guys, so when you do the calculations for these 2 very simple examples, those 2 very simple examples, let me just put them on the screen again. You just do those ones. It's just a simple homework, you don't have to submit it. Like I said, in the next lesson, that is when we are going to then do calculations. The next lesson, lesson 8, will specifically be just doing calculations on turning effect. We'll also look at the difference between moment and force and work done by a force, right? So I hope now we are able to describe the moment of a force, and if we just look at a simple machine, common machines in everyday life, we can now be able to say, okay, that's where the fulcrum is. The fulcrum and the pivot are the same thing. Okay, that's where the pivot is, that's where the effort will be applied, and that is the load. I hope that we're also now able to identify and say, okay, these are actually anti-clockwise moments and these are clockwise moments. Okay, so thank you very much guys for watching the video and paying attention. Thank you very much. We'll meet in the WhatsApp lesson. This is your teacher, Marshall A.C. Candiado. Thank you.